So my name is Khaled. Today I will present my recent work on supporting multicast forwarding for data center networks by relying on servers. So this is a joint work between myself, Parham, Yassini, and Mohamed Hefeeda at Simon Fraser University. So today's in many data center applications, many of them actually exhibit group communication patterns where we have a single source sending data to multiple receivers. This includes popular data processing frameworks like Apache Spark, for example. They support the broadcasts primitive to send data to multiple receivers. Also in recent distributed machine learning algorithms like parameter servers, where we have a centralized servers keep track of the parameter values, keep sending data to the workers, and then for them to actually update the values and send them back to the server, and so on. And also push-based publish-subscribe systems, where we have like a single message as well that we want to distribute to multiple receivers. Using the topic abstraction. However, these systems mainly rely on unicast, and they don't actually support multicast. However, these systems share the common theme, where they have a single source, probably a source VM, located at one of the servers, and multiple receivers potentially distributed across all the racks in the data center because of the VM allocation policies. So these applications could potentially benefit from a scalable and efficient multicast primitive in two actually main performance metrics. So if we are trying to plot the bandwidth and delay versus the receivers, if we have such a network primitive, then the unicast will scale linearly and for both bandwidth and delay as we increase the number of receivers, and multicast will basically will not increase ideally, or just increase a little bit compared to unicast, which again very beneficial to these applications and the network operators as well. As I mentioned, these systems unfortunately rely on unicast, and they don't support multicast. And more specifically, they actually currently, in the current multicast forwarding system, they even cannot support multicast because of the large-scale and multi-tenant environment that the data centers provide. And we actually have four main challenges for this problem. The first one is the large state size at switches. So as we increase the number of sessions, then this means more states that need to be maintained as switches, and also more switches need to maintain more states. Again, since we have limited memory and the SRAM is very expensive, then usually we'll not be able to scale up to 100,000 of sessions, for example. If we are trying to move some forwarding state to labels, then since we are working with a very large scale network, then the label size in current systems at least could be as large as the packet size itself, which is not very efficient in terms of bandwidth consumption. Finally, the third challenge is redundant traffic. So if we have a switch that's supposed to send the packet only to the two orange rectangles or squares, then actually some algorithms or some systems will actually forward the packets on other receivers because, again, they are trying to reduce the label size with the trade-off with more traffic sent to wrong receivers. Finally, many of these label-based systems produce variable size labels, which basically will potentially increase processing at switches compared to the just fixed label sizes. So all of these four challenges will result in reducing the number of multicast sessions and their sizes compared to the ideal situation if we had such a network primitive. So our goal is trying to design such an ideal network primitive or an efficient multicast forwarding system for data center networks. So the inputs to our system is the tree with the source and multiple receivers, again, potentially distributed among the racks in the data center. And we would like to design a data plane forwarding algorithm in the network to actually send the packets from the source to all of these receivers. So we design Orca. It's a label-based multicast forwarding system. Our design is based on three main ideas. So the first one, we move state to labels. This will make sure that we reduce the state size as the switches. But at the same time, we carefully engineer our labels so that we produce or design fixed size labels. And this will ensure that not just small processing switches, but only predictable latency and predictable processing at these switches. And more importantly, our core idea here is that we divide the forwarding function among switches and servers in the data center. And this, as we will show in a few slides, this will reduce the label size significantly compared to the other systems. So our design basically is leveraging the locality of racks, the availability of processing resources, and the extra or excess bandwidth within the racks. Orca has some nice features, like, for example, sustaining the high throughputs, maintaining small state at only a single layer in the data center network, and significantly reduce the label size, which reduces the bandwidth consumption, and totally eliminate redundant traffic. It does not actually produce any redundant traffic. So our key insight actually is coming from the key challenge. Interestingly. So the multicast basically in data centers get denser as we get closer to the leaves. So if we are, as we see here, we have a source VM and multiple switches till we have multiple receivers at the end. So if we start adding labels to present these leaf switches at the bottom, so we'll have a lot of label size. However, actually, all of these labels are not needed till the packet actually arrives to the leaf. So our approach is as follows. We divide the multicast trees into layers, and then encode links belonging to a layer into a separate label component. Basically, it's a kind of a bitmap representing the links to be duplicated to. And instead of representing all the leaf switches as labels as this, we actually design a new Orca label that is consisting of two components. The first component is called the source label, which will make sure that send the packets from the source VM to all the leaf switches belonging to the multicast tree. And the leaf label that is being transmitted in the network is just a placeholder. It's kind of an empty label. And the actual leaf label for each rack will be maintained at an Orca Agent, which our software component or our component that will be running at the servers. For example, here, if our session has 3 leaf switches with multiple receivers, then we'll assign multiple or 3 independent agents. Each one of them will maintain the actual leaf switches. So what will happen next is that the leaf switches, when it receives a packet, just like this, including the placeholder, it will forward the packet to the right Orca agent, and the Orca agent will just label the packet with the actual leaf label from its memory and forward the packet again to the leaf switch. The leaf switch then will duplicate the packet as expected to the final receivers. For this actually solves only the second half of the problem, which is the leaf layer. But we also need to maintain the same conditions or guarantees for all the layers, basically small size label and fixed size label at all the layers. And this is the role of the source label. So the source label first encodes the path from the leaf to the core. Since we only have a single path to the core, we can have a single port mapping using a fixed size number or fixed number of bits. And for the core downstream label, again, it follows the same idea. We have a single core switch, so representing multiple links, so we can represent each one of them using a bitmap. For the spine layer, which actually, or spine downstream layer from the spine to the leaf switches, we encode them using filters or like, for example, Bloom filter. And then we maintain all the false positives as a state in these switches. And this is where our small state will come in, so that we make sure that we do not result in any redundant traffic inside the network. To realize this system, we actually designed and implemented the Orca architecture. Given this data center network, our core component is the Orca Agent deployed at the racks. Then we have a centralized controller, which will be responsible on creating the labels, managing the session dynamics, and it also will communicate with the leaf controller to distribute the new labels. And the leaf controller will also be responsible to select or elect the agents from its own rack. And the agent has its own controller, which will manage the state and work with the leaf controller to elect a new agent. We also have data plane components across or in all of the network switches to process our labels, as well as the agent data plane component which will be basically responsible of attaching the labels to the packets. Our attaching or our data processing or packet processing algorithm is quite simple. That can be implemented on both CPUs and SmartNICs if a data center actually has these SmartNICs. To ensure that Orca can forward packets even when an agent fails, we also implemented or designed a fault-tolerant forwarding. And the main idea is that since we have a small state at each rack, we actually have the luxury to replicate it to multiple agents at the same time. And the leaf switch will be responsible to forward the packet to the active agent, to the active elected agent, or to multiple active agents if they want to round robin the traffic among multiple agents. In our system and in our paper, we only implemented the first option, but the system itself can realize the second one as well. In the paper, we have more details on how we update the agent state so that it remains consistent with the centralized controller, how we select the active agent, and all the data plane operations. And again, all of these details are in the paper. We evaluated our system in two setups. The first setup is using large-scale simulations consisting of a leaf spine topology with 27,000 hosts using 1 million sessions with different VM placement and allocation strategies. We compared versus the current state of the art, which is called Elmo, in terms of the session state, label size, and redundant traffic. Elmo is a label-based approach, and its main limitation is that it cannot maintain the trade-offs that I mentioned early on. And Elmo itself is configurable, so it has multiple configuration. In our paper, we actually evaluated our system against most of its main configuration. But here we will only focus on two main configurations that will show the spectrum of that space. So I will show multiple, or I will plot multiple results at the same time so that hopefully you get the idea of these trade-offs and how Elmo works. So first we'll have the label size versus across different data sets in our data sets. And these data sets are very important because they actually a proxy for different shifts in session sizes, as well as VM allocation policies that actually happening in data centers. We're actually plotting the session state versus the receiver density for a single data set. And we also measure the maximum number or the maximum percentage of the redundant traffic. So the first configuration of Elmo result in a reasonably large label size of 100 bytes. But unfortunately, it results in a lot of state at most switches. And they are doing this so that it can reduce or eliminate all the redundancy. To actually reduce the state, just like this, in another Elmo configuration, it results in even a much larger label size, up to 200 or even more than 200 bytes. And redundant traffic of up to 113% compared to the ideal situation. Compared to Orca, Orca basically result in a fixed label size in this data center of 19 bytes only, represented by this red line, with a very small state at just few switches in the spine layer. This value is not 0, it's actually 2, but again, because the range is very large, it's not showing here, with the redundant traffic of 0%. So basically, Orca storage scales very well compared to Elmo. We also evaluated our system in a testbed, so we implemented all of these components for example, the Orca switch implemented in native PGA, and it can be easily extended to use P4 if needed. So first, we characterize the benefits of Orca to applications. So we plot the communication time versus the workload size of a certain application, called LDA. So basically, we implemented an application that emulates the traffic of LDA application. So the communication time for unicast increases as we increase the workload size. And for Orca, as we increase the workload size, the communication time increases sublinearly or at a lower rate compared to the unicast. To actually compare this in terms of the number of receivers, we compared the unicast situation when the sender uses 1 core, and we also see that it increases linearly compared to the number of receivers. And even if this unicast tries to use more cores, which again, more cost to the operator, it's still not efficient or not ideal, as it still needs, or some cores still need to do some processing to send these packets to the receivers. Orca, since it's a multicast paradigm, it can reach this ideal case that I showed in slide number 2, where it actually scales very well in terms of the number of receivers. So for the sake of the time, I will skip the other results of the agent scalability, where we show basically that our implementation scales very well in terms of, for example, throughput, and it results in a predictable number of cycles per packet, as we have more active sessions managed by these racks. But in conclusion, Orca is an efficient multicast system for data center networks. The key idea is to move parts of the forwarding to servers. And compared to the Elmo, it's the only system that actually reduces both the state and the label size and eliminate the redundant traffic while maintaining very small processing at the switches with a very small processing resources at the server for an average of 1 to 2% for the total rack CPU resources. Thank you.